Good morning, and thank you so much for joining us for the November Town Hall for IGSHPA. Looking forward to a great presentation, and we really appreciate everyone who's able to attend today. Just a few quick things to run through on the IGSHPA side of things. So the latest IGSHPA news, this is our last Town Hall event for 2022. We really want to take a moment and just thanks to everyone who's attended our town halls throughout the year and any of our speakers that we've had. It's been wonderful and a great opportunity to get information out in front of all of our members. We do have one special event coming up. This is going to be the week of actually Thanksgiving, but we're going to do a 1-hour presentation with Charles Goulding of Energy Tax Savers to talk about all things commercial incentives. I don't know about any of you else, anyone else on the call today, but I get a lot of phone calls every day, it seems, asking questions about the federal incentives available, particularly as it relates to the IRA. So hopefully we'll be talking about Section 179D and all of the federal incentive dollars available. If you have any questions ahead of time for the presentation, send them along to info@igshpa.org. That would be great. Also, another reminder about another fun event coming up is our conference. We are having our 2022 conference this year in conjunction with National Groundwater again in Las Vegas. If you would like to attend, there's still plenty of time to register through our website, igshpa.org, and any of the information that you need is there. We want to take a moment and thank our conference sponsors, all of those listed here, particularly with our diamond, platinum, gold, and silver and bronze sponsors. We couldn't do this event without them, and we really appreciate all participation. So IGSHPA will also have some booth space available, which is great. Just as soon as you walk into the booth the show floor at the conference, IGSHPA's right there. So take a look, walk around, talk to some of the great vendors that we have that support our industry, and hopefully you'll make some new connections, meet some new faces. The conference program is now available online. So if you go to igshpa.org/conference 2022, you'll be able to run through all the presentations that are available for the conference. Just as a reminder, we are no longer waiving CEUs for your renewals. All of these town halls and dig deepers do count towards your CEUs for IGSHPA. But if you have any questions about your renewal, please go to the IGSHPA website or contact info@igshpa.org, and we'll be happy to help. So just a little bit of housekeeping. As a reminder, any questions that you have for our speakers during the presentation, please put those in the chat function. I will moderate those questions at the end of the presentation and ask them of our presenters. Any questions that aren't answered today that we see in the message, we will get answered later and then respond with those through email later on. But please make sure your microphone is muted during speaking. We will have a recording of this being posted on YouTube at a later date. One quick disclaimer and potential conflict of interest. The upcoming presentation represents the opinion of the presenter and does not represent any official position, opinion, or endorsement of any products or services by IGSHPA or its members. IGSHPA Town Halls and Dig Deeper webinars are for member updates and education on the latest information in the geothermal heat pump industry and are not meant to endorse one technology or brand over another. It is the presenter's responsibility to disclose any conflicts of interest or position that may arise in the content of their webinar. If you have any questions about that disclaimer, please, again, feel free to send an email and we will be happy to go through those with you. And now our speakers. I am so excited to introduce Gaylord Olson is an independent consultant and inventor with engineering degrees from South Dakota School of Mines and Technology and UCLA. He is a member of the Industrial Advisory Committee for Mechanical Engineering at Temple University in Philadelphia. He is the inventor and co-inventor of 12 patents and several recent patents related to multi-source heat pumps, underground thermal energy storage, and solar thermal energy collection. He is a member of the International Ground Source Heat Pump Association, New York Geo, ASHRAE, and the American Solar Energy Society, and the Northeast Sustainable Energy Association. We also have Dr. Yu, who earned his 2 master's degree and 1 PhD in architectural engineering, civil engineering, and computational science and engineering in 2008, 2012, and 2014, respectively. After graduation, Dr. Yu worked in industry as an energy engineer to perform building energy modeling and simulation. He is a LEED accredited professional and an ASHRAE building energy modeling professional. Currently, Dr. Yu is working as an assistant professor in the Department of Civil Construction and Environmental Engineering at North Dakota State University. So without further ado, I will stop sharing my screen and allow them both to present. One final thing for CEUs, if you would like your CEUs recorded for this presentation, just make sure that you mention that in the chat. Thank you.
Okay, can you still hear me okay?
Yes, we can.
Okay, yeah, would you like to test your audio and make sure that everything's working from your end?
Yeah, how about now?
Okay, everything is fine. I'm going to do the first part of this presentation, and then Dr. Yu will present simulation work near the end. Also, a lot of what we're going to present is already on a YouTube video, and there are two ways to get to that. There'll be a direct link at the end of this presentation, but you can get to it very easily with typing in 4 words: future methods for heating. The full title of that video is Future Methods for Heating and Cooling of Buildings, but you only need 4 words to get to it: future methods for heating. Anyway, next slide now, yeah. So this is just a kind of a definition that we use for multi-source heat pumps. Previously, we had occasionally used the term hybrid heat pump, hybrid instead of multi-source, but lately we're avoiding that because in Europe today, if you talk about a hybrid heat pump, they're going to think you mean natural gas along with a electric powered heat pump. And that's not at all what we're proposing to do. No natural gas in anything we're going to propose to do here. So next slide. As I said, I'm going to go over these kind of quickly, but the details already exist on another YouTube video, and we can also send documents. You'll notice some reference numbers at the bottom there. Reference number 1. What's presented on the slide here comes from 3 authors in Belgium. And the paper was done a number of years ago, but as far as I know, nobody has implemented it exactly like this. So basically, we're calling this approach preconditioning. And they have 2 separate bore fields. They're trying to keep one as warm as possible all year long, or at least warmer than the deep earth temperature. They're trying to keep the other one as cold as possible all year long, colder than the deep earth temperature. Although with geo-exchange, people like to say, well, we have a nice stable temperature underground. And yeah, that's pretty good, but it may not be as good as can be. So ideally, if you can do it, you'd want to have a warm temperature underground for the winter and a cold temperature underground for the summer. So let's look at the right-hand example here. That happens to be for the coldest day in the winter, or the coldest nights in the winter, whatever. The dry cooler is putting very cold water into the right-hand bore field. And at the same time, there's relatively warm water coming through a heat exchanger and into the heat pump. So the heat pump will boost the temperature, of course, and so everybody's comfortable, and you have a nice high COP for the system. In the opposite season, on the hottest summer afternoon, you'll have the valves and pumps arranged. Oh, by the way, there are multiple pumps here. You can't do this with only one source pump for the system. I'm not going to go into the details of all the valves and pumps here because there's a way to simplify that quite a bit. But what's going on the left-hand half of this screen is the hottest summer afternoon. So you've got nice cold water from the right-hand bore field, and you're preconditioning the left-hand bore field with the dry cooler. We should really call it an air to liquid heat exchanger. It's not only a cooler, it's a cooler and a heater, whatever you want. Now, they're showing bypassing around the heat pump. So they're getting water that's cold enough to not even bother with the compressor and the heat pump. So they've got the economizer mode operating there, which is kind of nice. Anyway, enough time on this one. The next one, yeah. Okay, these are multiple examples, all from people in Europe. The first one we refer to as the Belgian design. The number 2 here was done in a very complete way. This is a crude example of multi-source. In this case, they're not able to do preconditioning because they've got an air to refrigerant heat exchanger at the top of that block. And they put all of the elements in one box, which would have to be mounted outdoors in this case, because they want an air source mode. So they've got an air source mode with an air to refrigerant exchanger at the top. They've got a ground source mode with 3 ground boreholes at the bottom left. And then internally, they have 2 additional heat exchangers, one for domestic hot water, DHW, and another one for space heating and cooling. Now, this is a system that was actually very thoroughly designed, analyzed, optimized, and built. So the test results are all there for it. And I'd recommend people take a look if you have time to that reference number 2. Reference 3 comes from people in Italy. It was designed primarily for cold climates. And this does not have an air source mode. It's got solar thermal. And so there's a buffer tank that the solar thermal collector feeds into. And that in turn feeds into a heat pump to the building. So, but not only that, they've got 1 or more boreholes that are part of the system, makes it multi-source. And so on the hottest summer days, they've got really excess heat. They don't need any more heat. So they take all of that and warm up the region of the earth around the boreholes. So this prepares them quite well for the following winter. And if in the winter, if the sun is not out for multiple days or a week or whatever, no problem. They've got warm water from the boreholes that comes up through the tank in this case, and then to the heat pump. If they wanted to, they could have had a modification to allow cooling for this design also, but they were only choosing it for optimizing it for heating. So that's from people in Italy. The bottom right here is kind of brand new. It's a publication from only about a month or 2 months ago, September, I believe. Yeah. And again, it's multi-source. They've got an AHX, air heat exchanger, also called a dry cooler by some people. And they've got a BHX, borehole heat exchanger. Then they've got the box that selects which of those 2. They might be able to put them in parallel, but I'm not sure about that. So anyway, a water source heat pump. So everything we're doing assumes that we're going to have a conventional water source heat pump as part of what we're proposing here. I guess that's enough time here. Yeah, let's go along to the next. So here we have some direct quotes on the bottom from the, in the first case, reference number 1, from the people in Belgium that did not have an air source mode. They could not feed the dry cooler output into the heat pump. They had only preconditioning of 2 different bore fields. But believe it or not, the summation of the borehole length in both of those bore fields was 47% of what would be needed for a single bore field that was not multi-source. So this is something which I find pretty interesting, but if you have any doubts about it, I'd recommend you go back and read that document, reference number 1. Okay, almost the same thing. Reference number 2, they're stating that they can get by with half the size of a conventional single source system. And reference number 4 is the same thing again, 50%. They're reducing the bore field size by half by using a dry cooler or something equivalent. And so, and if you look at the capabilities of dry coolers for heat exchange, you find that they're in the range of hundreds of dollars per ton for the large scale systems. Borehole heat exchangers are on the order of thousands of dollars per ton for heat exchange. So this trade, even though it's a little bit more complex, it's people are finding, especially in Europe, they are finding that it's definitely worthwhile to do multi-source. So go on to the next one now, yeah. Okay, so now on the left here, we're showing the in a crude way, the examples from Spain and Germany on the left, where you can have either air source or ground source, but not preconditioning. The example from Belgium did not have an air source mode. It was only preconditioning into the left-hand bore field or the right-hand bore field. So in both of these cases, people are getting a 50% reduction in the ground loop size that would be needed for conventional single source geothermal. So to me, logic tells me that if you can have both of these in one system, you will likely get even better than 50%. It might be a 60% reduction in the bore field size. But there will still be a need for drillers and people digging trenches, because on the coldest winter nights and the hottest summer afternoons, you still want a bore field to take care of those extremes. So what we're proposing is something like what's on the right-hand side here. And it's got 2 variable speed water pumps and 3 valves and everything is computer controlled. The valves as they're configured here would have to have an internal design, which is called a T-port. You can also do this with L-port valves, just with a rearrangement of the back-to-back valves at the top there. So either L-port or T-port will work for this. So next one, yeah. So this shows the flow paths for the preconditioning capabilities of that design. Red for hot, blue for cold. So the left hand shows the valve settings for preconditioning for heat into the right hand bore field, and getting nice cold water for the heat pump. So you have high efficiency. And the opposite season is on the right, of course. And this is the coldest winter night. And you're putting really cold water into the left-hand bore field and getting nice warm water from the right-hand one. So this is equivalent to what was proposed by the authors in Belgium. So going on, yeah. Oh, I should add one more thing. There is at least one commercial, probably more than one, actually, but one commercial multi-source product that is commercialized, and it's a German company called ThermSelect. And if you go to their website, they are promoting their product as the most efficient heat pump in the world. So I guess that means that they're using less electricity and getting more heating and cooling from their system than what anybody else can do. So let's go on to the next one now, yeah. So that parallel mode, oh, yeah, the parallel, oops, back up one. I skipped over something. Okay, this shows the parallel mode functionality of the system. If we want to, when we have a similar temperature from the bottom block as we do from either the left or the right block, we can operate both of those pumps where the top pump is having twice the flow rate of the bottom pump approximately. And in that case, we'll get an equal flow from one of the underground blocks as compared to what's above ground. So we're calling this a parallel mode, and it gives a benefit in the transition range when the temperatures from two different sources are similar. And that shows up graphically on the next slide on the left. So advance one more, yeah. Okay, now there's a larger version of this. And oh, by the way, we have documents that explain all this in writing as well. So if anybody wants to, they can send an email or contact either of us, and we can send you the full documentation on what all is being presented here. So anyway, graphically, it shows that there's a benefit for heating in the middle region when you have similar temperatures from two of the blocks. The air source mode is shown at the middle here. So the ground is completely out of the picture, and we're only using the heat pump with the above ground thermal exchange unit. And the only reason we call it above ground thermal exchange unit is it could be solar thermal, or it could be air to liquid exchange, or it could be both of those together. But as of a year or so ago, we were assuming that everything will have to be above ground, and then another part of the system being below ground. But we're coming to think there's an exception to that statement, which we'll cover later. Now, if you have only one ground loop, you can still get a lot of the functionality with what's shown on the right-hand side here. The right-hand side is still multi-source. It's got a ground source capability, an air source capability, parallel, and with two water pumps, it can do preconditioning. So next slide, yeah. So going to something quite a bit larger scale now, you're not restricted to a single heat pump to operate this kind of a configuration. What we're showing here is 15 heat pumps in a 3x5 array. And the left-hand arrangement of pumps and valves and blocks are exactly the same as we've already discussed. And so we have all those different capabilities: air source, ground source from the hot side, ground source from the cold side, parallel, etc. But instead of feeding directly into one or more heat pumps, we're feeding through a product from Taco Comfort, which you can find on their website. Type in Twin T. You'll see what it is. It's a special type of hydraulic separator, and it replaces two closely spaced T's, which is a more conventional way to couple two loops like this. But the nice thing about the Taco Comfort product, it's fully symmetrical, so you can have flow in either direction, either in this design, either horizontally or vertically. It doesn't really matter if the flow is one way or the other. It works all the same. And that's kind of important for the rest of this system here. You'll notice that the 5 heat pumps in the three different vertical paths are connected with a single pipe distribution. Oh, and also this would be in the category of ambient loop or 5th generation heating. So basically, we're trying to keep the temperature for all the heat pumps in a very moderate range, maybe between 30 and 90 or 40 to 80 degrees Fahrenheit, in that ballpark. So the heat pumps will always have very high efficiency, no matter what or when. Now, if you have, let's say there's a primary loop which has that 4-way reversing valve right above the Taco Comfort Twin T fixture. The 4-way reversing valve and its associated pump provide the flow for the primary loop. And With the reversing valve, we can reverse that flow direction periodically. If we could not reverse that direction and we had the flow in the primary loop always clockwise, then the top 3 heat pumps in this array would always have the best performance. They would have the highest COP and the highest thermal capacity. The bottom 3 heat pumps would always have the worst COP and the worst thermal capacity. You can kind of do a brute force way to get around this by using high flow rates and big diameter pipes. But rather than the brute force way, I would suggest that it might be better to periodically reverse the flow direction so that almost once per day or once per week. And so sometimes the bottom 3 heat pumps will have the best results, and other times the top 3 heat pumps will have the best results. And so over a long enough time, everybody has just the same average COP and average thermal capacity. Again, these are all water source heat pumps, and we have those Taco Comfort Twin T fixtures located at every single heat pump location. Those heat pumps could be in every home along multiple blocks. They could be different zones in different buildings. They could be chillers instead of heat pumps. It would all be okay. So now, suppose we want 2 primary loops and couple them together somehow. We're proposing that can be done in a simple way with what we would call a donut fixture shown on the right here. And this is a very simple device. It's just a hollow donut that has connections at the top, the bottom, the east, and the west. It could be done using conventional plumbing fixtures like T-junctions and elbows. So you'd have 4 T-junctions and 4 elbows, and then it would be a rectangle rather than a donut shape. Either way would work the same, but it's symmetrical, same diameter pipe all the way around. So if you analyze this, what you'll find is if you have the same flow rate in 2 different nearby primary loops, you will end up with the flow going through both primary loops before it gets back to the starting point. In other words, if you try to follow a molecule of water starting in primary loop number 1, that molecule is going to have to flow all the way through primary loop number 2 and then come back and flow back to where it started in primary loop number 1. What that means is any large heat source or large cold source in any of those heat pumps or chillers is going to be shared with everybody else in both primary loops, not only one. What we did not show here is the need for isolation valves. But you would probably want to have isolation valves at all 4 connection points on that donut fixture. So go on to the next one now, yeah.
Gaylord, if you could wrap up in about 5 minutes so that we have time for
Okay.
Dr. to continue.
I'm going to go real quick then. I'm going to, this just shows a different configuration on the left, and everything else is the same. The next one. Okay, this shows only a single path vertically instead of the 3 paths that we had before. And we're showing the donut fixture there, coupling the loops together. We're showing hot loop on one side, cold loop on the other side, which would work, but it may not be optimum. It's better to probably have hot and cold on both, both primary loops. Okay, next one, yeah. In Denmark, people are using large solar thermal collector arrays and putting hot water into a large water pit, and they can feed very hot water near the boiling point off to multiple buildings in a nearby town. This is done quite a bit in Denmark. I'm not sure why it's not done elsewhere, but that's the way it is. So there's a variation of this which we're proposing on the next slide. And this would be kind of like a tank, but half the tank is above ground and the other half of the tank is below ground. And this might have some value. This uses a closed loop rather than the open loop that people are doing in Denmark. And we're showing a possible use of an unglazed solar thermal collector array on the top of this pond or water pit. So the next one, yeah. So another way to do this, which is fully explained in that YouTube video that I mentioned, is not to have explicitly a tank as such, but just to have a region underground which is enclosed with waterproof plastic liners. And so you can have a closed loop heat exchange in the middle of this region. And this would be kind of like a water tank, but probably less expensive, except for the excavation cost. Not too sure about that. So go on to the next one. So this is a graph which shows approximately what size you need to have if you want to do seasonal thermal storage, rather than thermal storage for a day or a week, but 6 months or 5 or 6 months of storage. This shows the case for a water, like water in a tank or a pit, and earth or rock or stone or whatever. This is a ballpark idea. So go on to the next one. So if you want to get the best result for a system design, you want to have the minimum total cost of ownership. And again, this graph is explained more fully in some of the documents that we can send out. But total cost of ownership would show the initial cost to build the system, along with the cost of electricity over many, many years, maybe 15 or 20 years of electricity use. So to be valid here, you have to kind of project what you think the cost of electricity is going to be for 10 to 20 years. And then that feeds into the overall design to get the total cost of ownership. In this graph, there'd be only one point which would have that minimum cost. It would be kind of a surface, if you like. So that would tell you then with multiple simulations what the very best size would be for the ground loop and for the dry cooler. Okay, go on to the next one. So really simple now. We can have designs that have 2 loops coupled together into a water source heat pump. The three right-hand examples here show the simple configuration. 2 water pumps, 1 water pump and a 3-way valve, or 1 water pump and 2 2-way valves. So we can select either of those loops, the computer-controlled valve probably is less expensive than especially a variable speed water pump. So the right-hand example here might be the preferred way to do this. Yeah, I was going to go into more detail on simulation for this kind of a thing. The next one, yeah. If you like, we can extend this to 3 different things. We're showing 2 loops, which could both be underground. Loop number 1 could be a borehole. Loop number 2 could be a shallow trench slinky design. Loop number, the other one, the dry cooler, would give a 3rd option there. Again, it's pretty simple to do this. Triple source rather than 2. Go on to the next one. This is just text which you can read. Basically, we're proposing now that with a trench design, we can have a quasi multi-source mode by having one heat exchange placed very low in the trench, the other one placed in a very shallow position in the trench. That shows up, I think, on the next slide. Yeah, so this is a very simple idea, but I don't know if anybody's ever done it, but it should work. We're proposing slinkies here, but it could be parallel pipes or whatever. So, and again, this is explained in a document that we can send out to anybody who cares. I think my time, one more. Oh yeah, one more, yeah. Or 2 more, the next one. The next one, I think, is my last one. We could do 2 different regions underground, one of which would be hot, one of which would be cold, And the hottest spot would be at the intersection points in these graphs on the left. So a hot intersection point and a cold intersection point. The right-hand picture here in color is taken directly from the website of a company in England called IGSHPA. And if you don't want to dig a deep trench, you can use an insulation layer. And then they're showing a snowmelt capability for that highway. And again, this was built and tested many, many years ago. So anyway, that's about it for me. Thanks for listening. Over to you, Yao.
Okay, so thank you, Gaylord. Yeah, I'm going to start from here, talking about a simulation case study by using the double layer underground heat exchanger system in a single family house. The house is assume that is located in Bismarck, North Dakota. With 2 floors, and the total square footage of the house is about 3,600. As shown in the figure on the left. And then in the case study, we compare a heat pump system using the used in the house with the 2 types of underground heat exchangers. The double layer underground heat exchanger is shown with 5 slick heat pipes at 2 layers. So one is buried right below the ground surface, called we call the upper loop, and the other one is buried underground at a depth of 8 feet. And 5 inches of rigid insulation are placed between them in order to minimize the interference between them. To compare with the performance of the double layer underground heat exchanger and 4 conventional vertical boreholes, considered as baseline. So the borehole depth is about 200 feet below the ground. So this slide shows the numerical models established in transit environments and 4 different cases you can see here in this, in the study. So the idea is to maximize the use of the lower loop for space heating, because this house is located in cold climates and is heating dominated building. So case 1 is to use the lower loop for space cooling in spring, because we'll use the lower loop for space heating in winter, as indicated in case 4. So after the whole winter operation of the lower loop, the lower underground region is cool enough. So it would help to maximize the cooling efficiency in spring, and also allows the transfer of some of the building heat to the lower underground regions, which is good for space heating in next winter. Case 2 is to use the lower loop or the lower underground region for space cooling in summer. So this is to make sure that the lower underground region is able to absorb more building heats that can be used in winter for space heating. Again, in case 4, where the lower loop is going to be used. And then the case 3 is to use the upper loop for space heating in fall season. The idea is to minimize the use of the ground where the lower loop buried before winter, to make sure that the lower loop is ready for winter in order to maximize the system efficiency for space heating in cold weather, because it is a heating dominated building. And the last case, we call the case 4.1, compares the results of the 2 underground loops, the vertical boreholes and dual layer horizontal loops with an air source loop for space heating in winter. So this is to identify how the dual layer loops are going to perform in terms of their heating performance when comparing with not only vertical boreholes but also air source loop in winter. So now let's look at some of the simulation result here. So the slide shows the cooling COPs of the heat pump for a typical day in spring, where the lower loop is used for space cooling. And as you can see, the cooling COP of the heat pump using the lower horizontal loop are higher than the vertical boreholes. And this is because after the whole winter operation, by using the lower loops, as you can see in case 4, as well as the cool ambient air temperature in spring, so the lower underground regions is cool enough. So it helps to maximize the cooling efficiency in spring. And this slide shows the corresponding cooling energy usage of the heat pump along with just daily average cooling COPs. So lower horizontal lobes, have a lower energy usage due to the higher efficiency and colder underground regions compared to vertical ones. So this result, therefore shows that we can meet the space cooling demands in spring for this house by using a lower lobe. Again, the idea of using the lower lobe for space cooling in this season is to allow the transfer of some of the building heat to the lower underground regions, so which is good for space heating in the coming winter. And then for the for space cooling in summer, the heat pump using the lower lobe can achieve a COP around 4.4 in the morning and then drops to around 3.5 in the afternoon due to the fact of the ambient air environment, mainly including the ambient air temperature and solar radiation. And compared with the dual loop system, the vertical boreholes have higher cooling performance. As you can see, the COP are more stable for the vertical boreholes, and the change only between the 4.0 and the 4.4 for COPs. So the cooling consumptions of these two systems are shown here, and they are very close to each other and for a given day in summer. So this result, again, demonstrates that the space cooling demands of the house in summer can be met, and when the lower lobe is used, and which has similar cooling performance with a conventional vertical boreholes. So this slide shows the heating COPs of the heat pump for a typical day in fall season, where the upper lobe is used for space heating. As you can see, the heating COP of the heat pump using the vertical boreholes are relatively stable, and is not affected by the ambient environments, ambient temperatures. The COPs of the upper lobe are slightly lower than the vertical boreholes, and the COPs increased in the afternoon because of the solar radiation striking on the ground surface, which temporarily increased the ground temperature near the upper lobe. So this slide shows the corresponding heating energy usage of the heat pump along with his daily average heating COPs. So the vertical boreholes, have lower energy use due to its higher efficiency, but the result also shows that we still need, we can still meet the space heating demands in fall and for this house by using the upper lobe closer to the ground surface. Again, the idea of using the upper lobe for space heating in this season is to minimize the use of the ground where the lower lobe buried, and in order to make sure that the lower lobe is ready for the coming winter in order to maximize the system efficiency for space heating. So case 4 results are shown here for space heating in a typical winter day. So the blue dots, shows the heating COP of the lower sticky pipes, and the green dot shows the COP of using vertical boreholes. So as you can see, they're very close to each other, and this is because of the use of the lower lobe in spring and summer for space cooling, and which allows the heat transfer and storage in the lower underground regions, as well as the use of the upper lobe in fall and for space heating, and which allows the saving of the heat in the lower underground region for use in cold winter. So the heating consumption of this, the two systems are shown here. So as you can see, they are very close to each other for a given day in winter. So which shows that the winter space heating demands of the house located in cold climates can be met by using the lower lobe, and it has similar heating performance. And this slide compares the heating performance of the heat pump when it connects with a dual layer horizontal sticky pipes, the vertical boreholes, and air source loop. For a given winter day, as shown, for this case, the outdoor air is too cold, which is around -10 Fahrenheit or below. So the air source heat pump is using auxiliary electric heater all the time, and which has COP equal to 1. So significant savings can be achieved by using either horizontal or vertical loops compared to the air source loop. I think that's these are the references we mentioned in this presentation. And that's all for our presentation. Thank you so much for your time.
Great. So we just have a few questions. Someone said that they've been researching geothermal for the better part of the year or so. They live in a hot climate, Florida, and wanted to know what they need better, or however, there's just not a lot of information about that. And I have a question that kind of ties into that. So looking at the huge differences in climate, so comparing Florida to your example here, quite a bit more north, do you find that the system is more applicable in loop field loads that are hugely different, or would you use something like this in something that has more of a balanced load?
I think we're okay with a balanced load for what we're talking about here. Many of the slides that I showed had a cold region underground and a hot region underground. So basically you can adjust the sizes of those two regions so that they will be adapted to whatever climate zone you are in. So I hope that answers part of that question.
Do you have an installation cost comparison between the cost of a conventional ground loop and then the hybrid multi-source model that you're displaying here?
We haven't gone into the cost comparisons a whole lot, but most people in the industry would say that for a given number of tons of heating or cooling, it's generally, if you have enough land area near a building, you're probably better off using trenches rather than boreholes. But to answer the question more directly, no, we haven't looked into much detail in terms of cost comparisons.
Okay, someone else asked, how are you isolating the heat loss when pumping heat into the ground bore for later use in heating? It seems like without insulation, you would lose the heat deposited due to entropy.
Sure, there's always going to be heat loss. What happens is that when you go to larger scales, larger systems, you have the opportunity to get to higher and higher efficiency for seasonal thermal storage. There's only one system in North America that I know about for efficient seasonal storage of heat underground. And they have 144 boreholes. They're not spaced 20 feet apart. They're spaced 6 to 7 feet apart. And it's at Drake Landing Solar Community in Canada. Been operating for probably 15 years now. They're very happy with it, but it was too expensive the way they did it. And they do not have heat pumps in their buildings. They have to keep a temperature that's high enough so that they have just heat exchangers in the homes, 52 homes. But that same, and also they have to have a connection at the center. So they keep the center point of their borehole array at the highest temperature. Now, the same thing works for cooling, and that's been demonstrated in Georgia. And you can contact Chuck Hammock. He will tell you how to do the same thing for cooling. So basically, if you want to do efficient seasonal thermal storage, you can do it. You're not going to insulate at the bottom or the sides of a very large region. But as the region gets larger and larger, the efficiency for storage gets better and better. And it can be you can retain maybe 50 or 60% of the summertime heat right into December and January. So I guess I covered that enough, I hope.
Another question, why wouldn't you manifold and valve control the parallel heat pumps in the large scale system to optimize the COP of each heat pump?
Yeah, you can optimize the COP of each heat pump. Well, wait a minute. Why wouldn't you manifold and valve control the parallel heat pumps in the large-scale system to optimize the COP of each heat pump? The concept that we have going here is that we'll have pretty much the same average temperature for all of those heat pumps. We hope that it's going to be a temperature which will give a very high efficiency, but we're not proposing to do anything independent. In other words, we're not able, in the design that we showed, we're not able to put hot water into one heat pump and cold water into an adjacent heat pump. That's just not the design that we have. So I hope that answers that question.
Next question, has cost comparison been made between slinky horizontal heat and borehole costing in cold climates like Vermont, and cost comparison between air source heat pumps?
I'm not sure about that. Yao, can you take a stab at that question?
I think, we are still working on that. We do see some savings, the operation savings, but we haven't, to put all the costs together to look at, the life cycle cost or cost of benefit, benefit year after year. But for sure that's some of the work we're going to do in the future.
How do parallel loops at different climates work in cold northern climates? Is horizontal loop integrity at risk of damage buried at only 6 inches deep?
I'll answer part of that. Of course, you need to have antifreeze to prevent freeze up for these. So that is a challenge. Hopefully someday we'll get better antifreeze capabilities that don't get syrupy at the coldest temperatures. But Yao, can you answer part of that question also?
Yeah, I think that's this idea is new, and there's supposed have some problem if we want to implement that. But what I can tell is we can bury the pipe near the ground surface. We can put the concrete driveway pavements on the top of that. So in order to protect this, so there's some ideas we can think about it.
Wouldn't the use of concrete on top, and you're going to drive over it, drive moisture into the ground and change the temperature expected profile that you'd anticipate, and therefore affect your efficiencies?
Yeah.
Okay, another question. If you wanted to consider a horizontal slinky loop, what depths would be necessary to perform as well as a borehole? And how much area would be needed for each 1 ton loop? We work in the upper Midwest areas, Iowa, Missouri, Colorado, Wyoming, etc.
Yeah, could you take a stab at that one?
Well, the depths of the horizontal loop, it really depends on location. And typically, if you're looking at the dew layers, for sure there's one of the layers going to near the ground surface. The other layer, we try to bury them as deep as possible, and typically below the frost line. And in this case study, we put the insulation between them, in order to minimize the interference between them, and also to try to save more heat in the lower ground regions. Regarding the boreholes, I think the typical borehole depth is around 200 feet to 300 feet, but it really depends on the ground formation. I saw some of the vertical boreholes, can go up to 400 feet down to the earth. But in our state, in North Dakota, we just go to up to 300 feet, because after that we reach the rock, and the drilling costs are going to be increased. But again, different locations, it really depends, and also depends on the thermal conductivity of the soil, and and we can tell how long the slinky pipes we need, and how deep the vertical boreholes we need.
I would agree. I think that I assume subsurface conditions affect the efficacy of all of these types of systems that you're speaking about today. Groundwater level, what type of soil that you're burying all of these in. I know that across the country, we're seeing depths as shallow as 100 or 200 feet, but to depths closer to 800 or 1,000 feet, really depended on space and the type of use. So I think that's very geographically dependent to answer that question, as well as subsurface conditions. So I would assume that that answer is really just dependent on the specific areas that you're working in. And even within those specific states, I assume geology changes pretty dramatically when you start to get below grade. Someone made the comment, antifreeze and top loop reduces efficiency by approximately 30. So effectively increases loop system by 30%.
I'll accept that.
Okay, I know I've heard repeatedly heat pump manufacturers complain that the use of glycol reduces the efficiency in the heat pumps. So I would assume that has a dramatic impact on your COP. In the simulations that you ran, did you assume glycol in that top loop?
At this stage, no, we just assume that is water.
Okay, great. Chuck Hammock did say that thanks for the mention. They have 4 cold BTS systems running at a marine base in Albany, and he will actually be at IGSHPA, so he's looking forward to seeing everyone there. So that is it for our questions. Do either of you have any parting statements or comments to make about your presentation?
I do have a comment on the very last things that we presented there. I came across some spreadsheet data that shows the number of hours per year that a particular place in North Dakota has, well, for each 5-degree range of temperature Fahrenheit. This happens to be Grand Forks, North Dakota, but it's not a much different temperature from Bismarck that Yao was simulating for. But here's the bottom line. If you can use that top loop that we're proposing for temperatures in the range of 25 Fahrenheit up to 60 Fahrenheit, you're going to have about 4,400 hours of time per year for that temperature range, which means that you can use that top loop for a much longer time than you'd have to use the bottom loop for heating. So, but basically between 25 and 60 Fahrenheit, there will be some heating needed for the buildings. Now, if you take the temperature range from 25 down to minus 30 Fahrenheit, then the number of hours is only 2,000 roughly. And so basically, you're going to be using or being able to use the top loop for about 4,000 hours. Use the bottom loop for only 2,000 hours of the year. Whereas if you had only the bottom loop, no top loop at all, you'd have to get all of your heating from that bottom loop, which means you're using it for 6,000 hours of the year. So this is a kind of a simple way to think about the dual slinkies in the trenches. We hope that we'll encourage some of you to give that a try one of these days. I hope that was clear.
Leads into one of the questions that just came in. Do you have modeling to accommodate subsurface conditions and geographic systems?
Yeah, you're the modeling person.
Yeah, I can, change the performance, the soil, the ground formations, there are different type of that and different thermal conductivities, in order to see how the results going to be changed. But it depends on where is the project located. But I can do that, yeah.
Great. One last question. How much area is needed per ton to install a slinky loop? Would you shoot for 10 feet or 15 feet deep, or would 7 feet be enough?
Like it, like the simulation, in the study, we have about the 4 times heat pump system, and the slinky pipe we use about 5,000 feet. And the trenches, if we're looking at the lower lobes, that's 8 feet below the ground surface, and the 5 trenches. So the length of the trench is about 200 feet. So something like that I can mention. So this is what we have for our case study.
Great. Someone did make mention that geothermal analysis software like thermodynamics, GLD, is available for use. And I would echo that for traditional geosystems to find out how much space a system would take up. There's lots of softwares out there that are available for you to model those, but I don't know of any that consider this type of technology with separate loops. But I'm sure that if you contact either one of these gentlemen, you could find that out later. With that, we will close for today. Just as a reminder, if you needed CEUs and did not mention so in the chat, to info@igspa.org is where you can send an email and let us know. As a reminder, we do have a special event coming up the week of Thanksgiving, so visit our website for more information, and then I hope to see everyone at the conference. Thank you both for presenting today and giving all the information that you had to us. It was great, and we will see everybody at the next event. Have a great day.